Hey, welcome to Transistor Biasing. This is BJT Universal Bias, also known as Voltage Divider Bias. So just like the previous bias configurations, we're going to analyze this circuit using Kirchhoff's voltage law. And with the universal bias configuration, we've actually got three complete loops that we can write equations for. The green loop is very similar to the base bias with the emitter resistor, so that loop should be familiar. The second loop, the red one, is through VCC, through R1 and R2. That completes a loop. And the third one is a loop that does not go through VCC. It's actually that closed loop in the bottom. So we're going to go through VBE plus VRE minus VR2, and we're back to where we started. So Kirchhoff's voltage law says that that should all be equal to 0. So we've got three voltage loop equations that we just wrote using this configuration. So out of those three equations, we need to pick two of them in order to move on to the next step of the analysis for the circuit. And it really doesn't matter which two we pick. I picked the green loop and the red loop for this example, but you can do it with the blue loop as well, and any two of the combinations will work. So we've got our two equations that we picked, and we need to get those equations in terms of current and resistance. So you can see there, I'm calling the current through R1, IR1, and we know that we've got IRE or IE through the emitter resistor. And in the other loop, we've got IR1 also and IR2. So now I've got my two equations. I've got them in terms of current and resistance. And this is the point where I'm always trying to target IB. And so I can quickly see that IE is equal to IB times beta plus 1, and I can substitute that in. And now I've got current and resistances. And everything up to this point is pretty similar to what we've done on previous biasing circuits, with the exception of this one up to this point has a second path that we're looking at. So the whole point of doing two loops for this circuit is so that we can eventually do our simultaneous linear equations and solve for our variables. But the problem that we have right now is that we've got three variables. We've got IR1, IR2, and IB. And in order to do the simultaneous linear equation, we really need to get it down to two variables. So we can look at our schematic and determine what IR1 is. IR1 is equal to IB plus IR2, and we know that because of Kirchhoff's current laws. Now you could substitute in IR1 into the two equations that we've solved so far, but that kind of complicates a little bit more because you're having to substitute into both equations. So what I like to do is solve for IR2, and then I only have to substitute into the red equation. And so IR2 is equal to IR1 minus IB. Now that gets everything in terms of IR1 and IB. So here's the math to kind of simplify things down and get all of my equations in terms of, I use a TI-89, so I need to get it in this format. I like to get it in this format, match up my IR1s, match up my IBs, and then get my voltage on the other side of the equation so I can just easily pop it into my TI-89 and solve for IR1 and IB. So here's the final two loop equations that we can now do simultaneous linear equation solution methods to solve for the IR1 and the IB. And now you could use the graphical method, you could use the addition subtraction method, you could use substitution, super substitution, but at this point for me, I'm just going to punch it into my TI-89. Now, once I've got IB, I can quickly solve for all the remaining voltages and currents. And as with any biasing circuit, I need to know where I'm operating at on the DC load line. So I've got to build that DC load line. And we've talked about this in the previous videos and how important this is. The DC load line and the DC biasing for a transistor is the foundation for your amplifiers.